So before we get into the procedure of how we design the piles foundations using the LRFD design, this presentation basically is to highlight the changes from the interim LRFD procedure to the new LRFD procedure for construction control. Right, to highlight those changes so that you know upfront that those changes. You're able to recognize from this presentation the changes of the modified Iowa ENR formula, right, from the interim LRFD to LRFD, as well as the changes in the WIP analysis. Right? And I'll show you a video of a step-by-step how you analyze using the WIP. Right? And this is the modified Iowa ENR formula. Under this column is the equation for a gravity hammer with wood, steel edge, or steel pipe piles. This is the equation you may be familiar with. Right? So this is the formulas using under this interim LRFD procedure. So the main change here is to remove the factor of safety 4 embedded in this equation and come up with this equation. Basically is to take 3, the coefficient, multiply with 4 and convert that resistance to a nominal resistance in the new LRFD design. All right? That's the main change. Right? Basically remove the embedded factor of safety of 4 and convert that equation to estimate nominal, right? No safety, but nominal resistance in this equation. If it's English unit, you take 3 multiplied by 4, that gives you the coefficient of 12. It's a metric, it's 2.5 multiplied with 4, and that gives you 10. The rest stay the same. You have WH, you have the set, you have the mass, the weight of the piles plus the weight of the cap. The rest of the definition of the parameters remain the same except the coefficient. Right? So the next one is, again, for different formulas for different hammers. It's gravity hammers for on concrete piles. Again, you take the coefficient of 4.5 multiply with 4 and come up with the coefficient 18. Right? And if it's in metric unit, 3.7 multiplied with 4, that gives you a coefficient of 14.8. Here is the equation to calculate, again, nominal resistance. Right? To distinguish from this and this one is the P. P is what we call the allowable, that included the factor of safety of 4. But rest here is the resistance N, which means that it's a nominal resistance. No factor of safety that included in this equation. Right? If you use diesel hammer on the wood or steel or pipe piles, as well as steam hammers, again the formulas that you're familiar with, multiply with 4 and convert to this equation, so the coefficient will become 12. Right, same thing, metric units, 0.25 multiplied with 4, and you have a coefficient of 1. Similarly, diesel hammer on concrete piles, 7 converted to 28, 0.58 converted to 2.32 by multiplying with 4. Right? These are the changes made. If you will use the Iowa ENR formula as your construction control, and determining the capacity of the pile during construction. How about WIP? What are the changes? Okay, so in the interim LRFD design procedure that you currently use, we define that capacity of the pile in terms of bearing capacity. Right? That with the factor of safety of 2.22, right? If you run the WIP, that embedded and define that capacity as a bearing capacity. Whereas in LRFD design, we will talk everything in nominal. Right? We will compare and calculate the values, every numbers in nominal resistance, nominal form. So you have 2.22 when you run the whip analysis as a factor of safety, whereas in the LRFD, you run the whip and generate the bearing graph in terms of nominal resistance. Right? So power is accepted if the measured driving resistance greater than the planned design bearing. Whereas in the LRFD design, power is accepted if the nominal, again nominal, measured driving resistance. Questions?
The question I have with the acceptance based on nominal measured driving resistance, are we going to get into an issue with when you write the specification with contractors as to not wanting to drive full penetration?
No.
Sometimes that's important for us from scour, and I don't want contractors thinking that they've done it just because they've hit that measured driving resistance.
So the questions is about whether the contractor will be driving at a different penetration based on this nominal or the acceptance criterion. In the following presentation, we'll show you the series of design example and as well as how we could determine the power performance. Although it's in terms of nominal, but the policy in Iowa DOT is to drive the power to the contract length. Still, although you achieve prior to the contract length in terms of achieving the nominal resistance. But the benefit of that is that you have, with the setup, you could reduce the chances of retapping the power if you could not achieve that capacity at the end of driving. We'll talk about that in the afternoon. Right? But still, power will be driven to the contract length. Right? That is part of the policy. I think it's still maintaining that policy by the DOT. But what is emphasized here is that we want to be consistent in terms of the estimation, the measurement, and we want to compare them in a same consistent manner. That if you estimate the capacity in nominal, we shall compare it with nominal, right? So in the interim LRFD design procedure, you do not need to perform the drivability analysis. Whereas in the LRFD design procedure, if you run the whip that I'm going to show you, you could perform the drivability analysis if you want to, but it's not required except if you have a structure resistance level at 3. Okay? And you use SPTN value in this as an input in the interim LRFD procedure for whip, but in the new procedure you use the unit friction determined from the Iowa design chart as the soil input parameters in the whip. Okay? And we'll talk about the soil parameters come with it, the soil damping as well as the creep value, and what are those values will be. I want you to refer to the volume 2, table 4.17. This is a reproduced and modified Iowa design chart that specifically suit for whip analysis. Right? What is the changes here is the unit of the numbers. Right? In the design chart, we have the unit in kip per foot. Because the whip is set up in a way that we will require the input as kip per square foot. So I convert those numbers in the design chart into this table that allows you to directly apply this table into the whip. Right? Refer to the table 4.17 for friction component, as well as table 4.18 for the end bearing. So in the design chart that you have, the unit could be in case I, but the input of the whip require them to be input as kips. So I convert them into kips that allows you, again, easily apply and input it into the whip. So refer to table 1.7 and 1.8 and do not confuse with the design chart they use for calculating the power capacity, but this is specifically produced for the whip analysis summarized in volume 2. All right, what are the changes in the soil parameters like damping and quick value in the whip analysis? So let's look at this damping that is currently used by under this interim LRFD procedure, that you have a range of a shaft damping and toe damping depending on the soil types. All right? So what will be the change is that we will have a much simpler shaft damping and a toe damping recommended by the PDI that's described in the help menu of the program, that is based on whether the soil is cohesive or non-cohesive, right? And the quick value is what is recommended by the PDI, Power Dynamic Incorporate, that developed the program. And this is the quick value. I think this is the same quick value that you use in the current procedure, but then the only difference is the shaft as well as the toe damping factors. So I'm going to run a video. Before that, I'm going to show you the project that I used to produce the video. It's a HP 10 by 57 pounds, 75 feet contract length, and beta 73 feet. Down Mac D19-42 is the hammer used. Assume a 7 feet stroke. Assume a nominal resistance of 200 kips for inspector chart analysis, and it is the procedure for the LRFD design method.
Open the WEEP program. You may see a default screen as shown. Select the unit convention. In this example, English units are selected. To begin a new file, select File and New. You can describe the project name, name your file name, and select the location where you want your file to be saved. In this example, the project is described as LRFD October Workshop-WEEP. File name is LRFD Oct Workshop-WEEP, and the file is saved in this directory. Press Next after completing this task. Select your hammer. In this example, a Delmag D19-42 is selected. Press Next after completing the selection. You may start the analysis with drivability. Press Next after the selection. For this example, an HP 10 by 57 steel pile is chosen. Steel is selected as the pile material. The contract pile length of 75 feet is input for the length. Cross-sectional area of 16.8 inches squared. Default steel modulus of 30,000 KSI. And specific weight of 492 pounds per cubic feet are accepted. For a pile toe in clay, a box area of 100 feet inches squared and a box perimeter of 3.33 feet are chosen. The pile size is 10 inches. Press Next after completing the pile input. For driving a steel H pile, hammer cushion is neglected here.
So I want to highlight that actually the hammer cushion should be included as part of the analysis. So I will revise the video, but in this example, the hammer cushion information was not included.
However, you could input the hammer cushion information if desired. Press Next to continue. The default resistance gain-loss factor of 1 is chosen for both shaft and toe. Press Next to continue. This page provides you some comments about your input. Also, you could click back to edit your previous inputs. After confirming all your inputs, you can now select Finish. This page allows you to input the geotechnical resistance distribution. The unit shaft resistance and toe resistance are selected from the Iowa design charts. In this example, the first layer for a depth of 6 feet is a soft silty clay with an average SPT end value of 4. The unit shaft resistance is determined to be 0.24 kips per square feet. The second layer down from 6 feet to 15 feet is a silty sand. The unit shaft resistance is determined to be 0.36 kips per square feet. The third layer from 15 to 23 feet is a firm glacial clay. The unit shaft resistance is determined to be 0.58 kips per square feet. And the fourth layer from 23 to 88 feet is also a firm glacial clay. The unit shaft resistance is determined to be 0.96 kips per square feet. Note that the shaft resistance distribution at each layer is assumed to be uniform. Since the SPT end value of 12 at the fourth layer near and below pile toe is too small, no toe resistance is considered here. The other parameters such as the quake and damping will be considered later. Next, select View and click on Main Input Form. On the Main Input Form, you can view all your inputs: your project description, hammer and cushion information, pile information, resistance gain-loss factors, analysis type on the upper right-hand corner, and a cross-sectional view of the hammer soil pile information. Next, select View and click on Depths Modifier Input Form. This form allows you to perform analysis at your selected discrete depths. You can choose an increment. For example, a depth of 5 feet is chosen. Add rows or the depth down to the actual embedded pile length of 73 feet. Next, go back to the main input form by selecting View and click on Main Input Form. Note that now the pile penetration is 73 feet with an exposed length of 2 feet. On the main input form, input the soil parameters following the recommendations given by the WEEP Help Manual. Select Help and click on Help Topics. Go to the Index tab and type and select Soil Parameters. And then click on Display. Scroll down the page, you will find the recommendations for soil quake and damping values. For this example, the shaft quake of 0.1 inches and toe quake of D over 120, which equals to be 0.08 inches, are selected. The shaft damping for cohesive soils of 0.2 seconds per feet and toe damping of 0.15 seconds per feet are selected. Close the help page and input these values on the main input form. Although the drivability analysis does not require these soil parameters, they are required in the bearing graph analysis that is described later. Save your drivability file, select File, and click on Save Input File As. Go to the directory and type in your file name. To perform a drivability analysis, select File and click on Analyze Input. At this point, the drivability analysis is being performed. Press any key and return to the main input form. Select View and click on Output. Next, click on Drivability. The drivability outputs show the ultimate pile capacity, hammer blow counts, stresses, stroke, and hammer energy versus depth. This information shows the pile responses during driving. Also, the driving time and total blows are estimated. Close this output and go back to the main input form. The next analysis is to generate a bearing graph. Go to the upper right-hand corner of the screen and pull down the Drivability tab and select Bearing Graph Prop Shaft Resistance. Adjust the range of loads in the bearing graph. Under the Ultimate Capacity, select Action and press Reset. If you want an increment of 30 kips, type 30 and press Enter. Adjust the shaft resistance percentage from the drivability analysis. For this example, the percentage is 100. Select Option and click on General Options. Select the Stroke tab and Single Analysis with Fixed Stroke and Pressure. Press OK and return to the main input form. Change the hammer stroke to 7 feet. Save your bearing graph file. Select File and click on Save Input File As. Go to the directory and type in your new file name. To perform a bearing graph analysis, select File and click on Analyze Input. At this point, the bearing graph analysis is being performed. Press any key to return to the main input form. Select View and click on Output. Next, click on Bearing Graph. The outputs show the ultimate pile capacity and stresses versus blow count at a fixed stroke of 7 feet. Close this output and go to the back to go to the main input form. The next analysis is to generate an inspector's chart. Go to the upper right-hand corner, pull down the Bearing Graph Prop Shaft Resistance tab, and select Inspector's Chart. Specify the target nominal pile capacity, for example, 200 kips. Save your inspector's chart output file. Select File and click on Save Input File As. Go to the directory and type in your new file name. To perform an inspection chart analysis, select File and click on Analyze Input. At this point, the inspector's chart analysis is being performed. Press any key and return to the main input form. Select View and click on Output. Next, click on Bearing Graph. The outputs show the stroke and stresses versus blow count at a fixed nominal pile capacity of 200 kips. Close this output and go back to the main input form. You've performed 3 analyses and obtained respective outputs. You can choose to rerun the bearing graph analysis at a different hammer stroke. After completing all analysis, select File and close the WEEP program.
So that is the video show the WEEP analysis based on the LRFD design procedure. And open for questions about the construction control.